Our next speaker is Kalina Nedkova, who will talk about a unified view of chemical enrichment in galaxies enabled by Slitless spectroscopy.
All right. Hi, everybody. Yes, my name is Kalina Nedkova. I'm a staff scientist here at Caltech IPAC. And I work on the Roman GRISM and PRISM data processing system, which means that I spend a lot of my time thinking about slitless spectroscopy with Roman. And so I'm super excited to tell you today about the amazing work that we're doing with JWST slitless spectroscopy and where Roman will take us in the very near future. So the work that I'll be presenting today is enabled thanks to the Passage collaboration. And in particular, I want to highlight contributions from Mark Rafalski and Farhan Hassan, as well as the Passage team. All of the people here in orange are here in person at this meeting, so if you want to ask us about Passage, please do. We would love to chat with you. And so GRISM observations are fantastic because you get a spectrum for every single object in your field of view. So you can see here that every single galaxy here is dispersed along a particular direction. And if you look very carefully, you can already begin to pick out some emission lines by eye. Okay, so we're not reducing these data. We're not, looking at 1D spectra. Just by eye, you can already begin to see, for example, right here, that's probably a beautiful O3 and H beta line. You see a lot of other very nice emission features. And so these data are really, really powerful to study galaxy evolution. So I want to tell you a little bit about the Passage survey. So Passage is a pure parallel program, which means that we took our observations at the same time as other programs. And so this is a really great way to maximize the scientific return of the mission. But it also means that we were restricted to only change setup when the primary program was doing the same. And so of the 63 fields that we observed, which you can see distributed here, we actually observed 15 within Cosmos because it turns out that astronomers like to look in very specific parts of the sky. So 15 of our fields are in Cosmos, but because we were restricted to, I clicked something wrong. Okay, because we were restricted to only change setup when the primary program was doing the same, only 13 of our fields have all 3 GRISM filters, and you can see a breakdown of the other fields as well. Okay, but one reason to get really excited about Passage is because you can think of it as a pathfinder for Roman. So here I'm showing you the transmission curves of our 3 JWST nearest filters. And here's Roman. So you can see that these are very similar in wavelength, which means that a lot of the science that we're doing with Passage, we will be able to do with Roman over vast areas. And this is what our spectra look like. So this is one emission line galaxy at a redshift of 1.8. You can see these beautiful booming emission lines. You see O3, H alpha. We also get a little bit of the continuum here that you see. And so this is really powerful if you want to look at metallicities of galaxies because you have the strong lines. So you have O3, H beta, and O2. Oh, and I also want to advertise that the code that we use to fit our spectra is now publicly available, and you're welcome to use it. So if you have questions, please reach out to me. I would love to get more people using this code to fit 1D spectra. Okay. And so the reason why we want to study galaxy metallicities is because they tell us something about the baryon cycle, which I'm showing you here. So Phil did a fantastic job of showing us how when you look at a simple picture, And then you dig into the details, you begin to see that things are really messy and complicated. And this is definitely true for the baryon cycle. But briefly, what I'm showing here is that you have filamentary accretion of metal poured gas from very far away from the galaxy. And this gas gets accreted onto the central part of the galaxy, which is here in the innermost 30 kiloparsecs or so. This metal pore gas then triggers star formation within the galaxy. And the stars that are formed as a result of this star formation synthesize heavy elements and they enrich the interstellar medium. And then you also have outflows driven by AGN or stellar feedback, which expel the gas away from the galaxy. But the picture is more complicated. Some of this gas is recycled back onto the galaxy. And these processes don't necessarily happen one after each other. They can happen at the same time. So this is very complicated, and it's very tricky to model. But one thing that I hope we can agree on is that these processes depend on the mass of the galaxy. And this is because if you have a very massive galaxy, it's going to have a very deep potential well, which means that it's going to be more efficient at accreting that pristine gas, and it's going to be also less efficient at driving that enriched gas back out. And so we might expect that more massive galaxies are more metal-rich. And in fact, yes. So this results in what is known as the mass-metallicity relation. Galaxies that are very massive tend to be more metal-rich, and then vice versa for the low-mass galaxies. And this is a result of the baryon cycle. And so when I say metallicity, I just want to mention that I mean the abundance of oxygen relative to hydrogen. You'll see it written in this way going forward. And one other thing to note is that the baryon cycle should also affect galaxies' morphologies. And so there might be some kind of link between the mass-metallicity relation and morphology, and this is a project that we're working on as well. Okay. So when we look at the mass-metallicity relation, of course, it's never as clean as one single line, but this is sort of a compilation of some previous results. One thing that I want you to notice is that really the JWST data are enabling us to reach the slow mass regime, which was not possible before JWST. And here are our passage galaxies. This is just a subsample of them. And you can see that they fill in the space very well. We have some low mass galaxies, and we also have some high mass galaxies. But if we want to understand these galaxies as an ensemble, we need to stack them so we can understand how galaxies of different masses evolve on this relation. So that's what we did. So at the very top, you can see our full sample of 731 galaxies. And then going down, we're going down in stellar mass. And you can see some really cool things here. For example, you can see evidence of the mass-size relation. So you can see that these emission lines are getting broader as you go up to higher masses. Another thing that you can notice is that the H-alpha line gets much stronger relative to the O3 line for the more massive galaxies. And so there's a lot of very cool physics in here. But so if we take our relations from before and we plot our stacked results, what we find is very good agreement with previous HST work. And so recent JWST studies have been suggesting that there may be some kind of flattening in the mass-metallicity relation, but for our results, we see no evidence of this using very large samples. And so I want to touch on what we can do with Roman. And And so if we take the deep tier of the high latitude wide area survey, this survey will, so with Roman, with the wavelength coverage, we'll be able to look at metallicities at redshifts of 1.7 to about 3. And then if we play a game and we take the stellar mass function times the detection rate, we can get a rough sense of the number of emission line galaxies that Roman will detect. And if we take the line flux sensitivity as well as the O3 star formation rate relation, we can work out that Roman will detect about 500,000 galaxies with O2 emission lines. So that's really exciting. And so if we just plot this, so this is, again, just a cartoon of the mass metallicity relation, but here I'm showing you the number of detected galaxies with Roman. You can see that we're really going to sample the high mass end extremely well. And for a subsample of these galaxies, we'll also have very nice deep imaging, which will allow us to look at the connection between morphology and metallicity. And then here are, this is the entire passage sample, okay? So this is going to be an entirely new regime where we're going to have so much data. And so I hope that we're all really excited to get our hands on Roman spectroscopy. But one thing that I'm worried about is that we can misidentify the emission lines that we measure. And so here I'm showing you work that was recently published where we took the spectroscopic redshifts that we measured from passage, and for the fields that also had photometric information from Cosmos, we used the photometry to derive the photometric redshifts of these galaxies, and so we compared the spectroscopic redshift to the photometric redshift. And what's really striking here is that you see that most galaxies lie on the one-to-one line, which means that we're correctly identifying the emission line. But you also see that you have these off-diagonal lines where the emission line has been misidentified. And so as part of the, oh yes, so up to 20% of single-line emitters are misidentified. And so as part of the GRS PIT, we are working on understanding how the line misidentification, or what I'll call line interlopers, and noise interlopers can affect the clustering that we measure with Roman. And so for now, we're finding very encouraging results that there's no shift in the BAO peak, but this is still very preliminary, so stay tuned. Okay, so I'll pop up my conclusions, and thanks for listening.
All right, thank you, Kalina. We'll take one question while maybe Vihang comes down.
So in terms of getting the photometric redshifts, I mean, there'll be LSST data. I mean, Jesse gave a talk yesterday. Is that a direction forward to resolve those misidentifications?
Yeah, so yes, absolutely. Thanks for bringing that up. We absolutely have to use the photometric data to inform our spectroscopic redshifts for Roman. I think that's going to be really critical. Okay, thank you.
All right, let's thank Kalina again.